Okay? So we want to talk, just in terms of geometric properties of graphs, about continuity and uniform continuity. Okay, so we have here a graph of some function, probably some power function, maybe exponential, plus or minus a constant, in an interval from A to B. And we're going to talk about continuity on this interval. So we're going to make this a closed interval. From A to B. We're going to establish that if the function is as pictured, we do have uniform continuity. Okay, so to find uniform continuity, it says, well, first continuity. Pick your epsilon, you find your delta. Your epsilon is how close you want the value of the function to be when you restrict the value of x by delta. How close the value of the function is going to be to its value at a point when you restrict delta. Now, I'm not going to write out all the words. You can reconcile this with the definition of continuity. So here I'm going to do this. Okay, pick epsilon. Okay, well, here we go. Here's my epsilon, indicated by this little arrow. Okay, and we're going to find, well, we're going to see what it means for this thing to be continuous at B. Okay, well, here's the vertical line where x equals b. Here is f of b, the value of the function at b. And by continuity, we want to restrict, by restricting the values of x to be close to b, we want to restrict the values of f of b within epsilon. So f of b has to be restricted within epsilon. So I'm going to put an interval here, an epsilon interval up and an epsilon interval down. And I'm going to project over here. Okay, so I want the values of the function to remain within this interval. Well, that happens as long as I restrict the values of b to be in an interval no bigger than this one. So anytime, values of x, I restrict the value of the function to be within this interval of the value at x equals b. Okay, I do that by restricting the values of x to be within this interval around b. Okay? We can see a couple of things. The function's getting steeper and steeper. And you can think about why, but I've exaggerated a little bit, but this projection line is closer to the projection line I used to find the value of f of b than this one. In other words, b is not right in the middle of the interval that I've created here. Okay, well, that's all right. I'm just going to pick my delta to be small enough that anything within delta of b is within this interval here. So I'm going to let my delta, I hope I've got a fairly sharp point on this chalk. Okay, there's my delta. And it's small enough that any time x is within delta of b, f of x is within epsilon of f of b. Didn't draw that very well. Now I can project this over here. Project this point corresponds to the value at b minus delta, and I can project this point. Corresponds to the value at b plus delta. And I can kind of then magnify my picture. Here's my f of b. There's epsilon, f of b plus epsilon, f of b minus epsilon. So that f of b minus epsilon, and my x interval over here here's b. Here's the yellow projection line. Okay, so I could say that this is, in a sense, this is a one-to-one function. This is like f inverse of f of b minus epsilon. In other words, you just take the f of b minus epsilon, you project this over. This is the point that comes down to here, and this point comes down to here. And this would be like f inverse of f of b plus epsilon. Now, your function doesn't necessarily have to have an inverse, okay? So you're not going to use this notation in any kind of a proof, just to get a feel for where things are. And then I've got my delta interval here. So I've got a plus delta here and a minus delta over here. And now I project these up to the graph, and they project over here. Like so. So that the value here would be f of b minus delta. That's f of b plus delta, sorry. And here, f of b minus delta. It's kind of an important picture. Now between this point and this point, you can imagine where that would be on this graph. There's a line segment. The line segment has a slope. And that slope is equal to the derivative of f of x at some x between here and here, some x within delta of b. So some x in the interval b minus delta b plus delta. So that the slope is approximately equal, well, actually it isn't. Okay, I'm gonna stop here because I want to think about exactly how to incorporate what I was about to say. Because what I was about to say wasn't going to quite be right. And what I'm getting at is, yeah, I can say it. Let's forget that I said this. Okay. Choose delta to be less than epsilon over the maximum slope. I think I'm saying that right. I'll fix it if not. Okay? Where the maximum slope is the maximum slope that you have within this band here. Okay? I could draw a picture, probably should. Okay, I'm going to draw my epsilon interval here. I'm going to draw my delta interval down here. Or my x-axis down here. And my delta interval will be something inside of the interval from this point to this point. Okay. Delta is any interval. A delta, and here's B. And here's F of B. Now I've got a slope here. And this slope, you can see, is pretty close to f prime of b, right? This function, as I've drawn it, has an increasing slope. And I want to just confine us right now to a function with an increasing slope. Okay? If the slope is increasing, implies that the slope I need a notation for this point. Okay, well, I'm going to do my delta interval here. Slope at b delta is greater than the slope, greater than or equal to the slope at any x in the interval I think I want an open interval here, b minus delta to b plus delta. Okay, because of course b plus delta is the maximum value of x within the interval. And the slope is increasing, so the slope's going to maximize at the maximum point in this interval. Of course, there isn't a maximum because it's an open interval, but certainly the slope at b plus delta, which is a little bit beyond the end of this interval, or beyond any point in this interval, is going to be greater. Now, I'm waving my hands, so we can do that with tight notation, but I want to keep this as conceptual as possible. Okay, so increasing slope implies that the slope at b plus delta is greater or equal to slope, any slope in the open interval. And in this case, if it's increasing, it's actually just greater than. Okay, it follows that the slope, and let's say the curve is doing this. Of course, I'm exaggerating this, but let's say the curve is increasing. Okay. Then I've got this interval here, and I've got a slope on this interval. And this slope is going to be less than this slope. Okay, so if this slope is less than this slope, and f of b, we'll put f of b here because I've exaggerated the slope, and f of b is here, trying to say it without notation, I just about need notation. It's f of b plus delta. Then this is clearly true, okay, because f of b minus delta is this, f of b plus delta is this. Subtract the two, you get the rise of a triangle from here to here. And the triangle has width 2 delta, so the slope of this triangle has to be less than this maximum slope, which is the slope at b plus delta. I want to write down an f prime of b plus delta, but I'm not going to do that. Running out of room here, so f of b plus delta. Of course, f of b plus delta minus f of b minus delta is just the width of this interval here. And you know, I don't want to use that interval. I want to use the half interval here and the half interval here. But I'm going to kind of leave that something for you to patch up. Okay? Okay, so this minus this is less than or equal to 2 delta times the maximum slope. And the width of this interval is the maximum slope times 2 delta. So the width here is actually less than 2 delta times the maximum slope. Which, if it's modified just a little, because I chose the wrong interval, I could do this on half intervals, I conclude that this implies this.